My name is Dan Bowers. Sadly, I'm a marketing guy, but I'm a former engineer assigned to the blade system team, so I work on the blade development team.
James Singer, blade system engineer. This is my lab. We do really just technical presentations, focus on technology with a competitive flair. As you can see, there's a lot of competitive gear in the lab, so we do talk about our competitors from a technical standpoint. So.
I gotta hand it to you, James. I've never seen this lab looks this good.
Well, we have to thank Chris Bradley for that one because he came in here during the Christmas break and he pulled everything out and it was on the table and we cleaned it out. So yeah, it does look nice.
So, what are we going to talk about? We focus on technology. We focus on the technology that's part of the servers and infrastructure that we do. We developed that balanced architecture that we've been talking about this morning. So our agenda for the next
hour and a half or
so. Okay,
yeah.
all right.
Is going to be based on what you guys want to hear about.
I will have to be USB cable for an hour and a half.
As an engineer, this is my favorite tool, which is the marker, and we're going to write down what all you guys want to talk about in terms of technology, servers, futures, how blades work, even competitive topics, and then we're going to talk about those things that you guys want to talk about in terms of this room. So, knowing that we can talk about servers, storage, networking, blades, memory, processors. We've got some demos going on in here. What kind of things did you guys come to Houston hoping to hear about in terms of Proliant? I know Martin wanted to hear about firmware.
Yeah, but then that's just me.
We can talk about how we develop our balanced architecture, AMD, Intel. We could talk about memory, low end all the way to the high end. We can talk about how Calvin's going to store his entire MP3 library onto a single blade. Ideas?
It's a big library too. So.
Let's start then with something related to balanced architecture. I know a couple of you guys have been server admins for a little while. 4 years ago, right here. 4 years ago, if you were a server admin, you'd probably be using one of these. That is a most popular DIMM 4 years ago. It's what size is that?
512.
512 megabyte DIMM. So if you wanted a server that had, let's say, 32 gigabytes of memory in it.
Yes, you did an awful lot.
Here's your 32 gigabytes of memory.
But I also remember if you did turn around and say, can I have 32 meg of memory, you either bought very small chips or you mortgaged your house and bought the 2 gigabit chips on the basis that that cost the same as a car.
These might have been 512 meg technology, 512 megabit, to do the 512 gig sticks. Well, memory has changed a lot since then. In fact, as of today, this is something new. I can now get this 32 gigabytes of memory in one stick. There's a 32 gig DIMM. Currently available, just available as of today on many of our Proliant servers, including the DL380 G7 and the BL460C G7. That means I've got a 2-socket half-height server in here that can put 384 gigs of memory. So compare that to what we were like 4 years ago. Part of the change in technology that's happened, that's driven the demand, not just for memory, but for other aspects of the balanced architecture that we design our server.
In fact, if you want to look at terms of power and cooling savings, the best power and cooling savings you could implement is not having the hardware even running. So I've done enough power testing on DIMMs to know that this 512 meg DIMM is probably anywhere between 8 to 12 watts, DC per DIMM. and you multiply that by 64, that's going to be a huge power penalty versus, say, the 32 gig. So 32 gig, I've not done power testing. I don't know what it is. It's probably right around 15, maybe 17 watts per DIMM, but you need a whole lot fewer of those than you do these guys. So just by keeping up with the technology allows you to be more efficient, make better use of your power and cooling budget.
Memory is just one of the things that's changed over the past 4 years in terms of what a server needs in order for a totally balanced architecture. Partly driven by virtualization. What a server needs in order to deliver its compute, you've got to have memory, and demands are going up and up and up for memory, more memory capacity, primarily delivered by larger DIMMs. Has been over the past 4 years. You've got to have CPU. Faster and faster, more core counts on your CPUs, delivered by the latest and greatest Intel AMD x86 CPUs. There's a 12-core AMD Opteron processor, and I think that's a 6-core Intel 5600 series.
Yeah.
Core counts keep going up, memory capacity keeps going up. But there are other aspects to a balanced architecture, and if you only improve these two things, you're not going to be able to deliver more computing power because
This is the 6-core.
the I/O bandwidth that has to come off that server also increases as you increase the memory and CPU capacity of that server. There are other aspects to this balanced architecture. James just pointed out one. I'm going to draw one over here, which is actually power. Compute requires power. Applications require power. So you're going to have to be able to scale power in order to deliver that balanced platform. So we've been attacking all 4 of these areas as well as some other aspects. I only do 4 because I can only draw 2D.
So you draw 3D.
Where's your storage?
For storage. It's an interesting
Or did you
question.
give it all to Kellen?
Partly, there's some storage inside the server, and that, in fact, has been growing with direct attached storage for the server. I'll give you an example of something else that's available as of today, which is direct attached blades, half-height storage blade with
You might as well just wait a second, because nobody's watching. I needed a tripod.
now that's some balanced architecture right there.
Steady hit. The other one?
The other one.
It's like a steady cam.
Fortunately, we get often in this enclosure, we get the equipment that was shipped to Mexico City and fell off the back of the truck once.
Yeah, we get the early prototypes.
That's enough.
There you go.
Sorry for the bounce there. You were on
12 hot
Jeffrey's
plug
side.
hard drives, all accessible while the system is running.
So it's got an outer sleeve and an inner sleeve, and the inner sleeve pulls out, and it's connected through a coiled ribbon cable, and that extends out. And since we use Aggie Maroon hot plug designation, it's all hot pluggable. So the real estate the slot real estate was very expensive. So the 6-drive model wasn't as popular because it was too expensive to have just 6 drives, and now we've doubled the capacity, or the hard drive capacity, or the number of drives in that same space. So it becomes, something a little more attractive, more cost-effective.
Now on the rack side, we do similar things like the Gary mentioned earlier, the DL180, which is a 2U rack server, which in addition to the standard 2 processors and networking, you can also fit to the 12 or 14 of the large form factor hard drives into the server itself. So for that storage, which is direct attached and goes in the server, we've been increasing that, and of course, hard drive capacities themselves have been growing from back when we had megabyte hard drives into now, I think the small form factor hard drives go up to 600 gigabyte, and the large form factor go up to 2 terabyte now. But a lot of the server, especially for the enterprise, is actually delivered over the fabric. So in order to deliver that SAN-like storage, basically the pipes have to either increase the number of pipes or increase the width of the pipe in order to deliver that increasing amount of storage. Which is why in our balanced architecture, whatever server we deploy, whether it's a rack server or a blade server, we have the ability not just to have, say, a single 10 gigabit pipe to your storage, which might be fine for some workloads. We have the ability to add additional 10 gigabit pipes to the individual server, by either adding network cards or mezzanine cards to the server. Because today you might be running 30, 40 virtual machines on an individual server, but 3-4 years from now you're going to be running hundreds of virtual machines on an individual server. So the hardware that you deploy today is going to be able to have to support hundreds of virtual machines. We're going to have processors that are going to be able to do that. We're going to have memory that's going to be able to do that. You're also going to have that I/O, which is why you want to.
It's a smart server. It's in the 80% band.
Okay. All right, good guess.
That's pretty
Yeah.
good.
80-20 rule, what does that mean?
Well, that you want to do, you want to spend the most time doing.
Blade. It's your flagship product, and every company has got a flagship blade. And in our case, what is our number one? What is our number one blade in our entire portfolio? Any guesses?
460.
BL460. Yes. Give that man another donut,
Yes.
or not? I don't know.
Or Diet Coke.
Here's a partial.
All have that. Dell has the M610, IBM has the HS22, and Cisco has the what is the B200 or the B200, their half-pipe blade. So they all have their their flagship product. So what makes it a generic utilitarian sort of blade? Why do people pick it?
A dual socket,
Yes.
Yes.
memory support, and the number of bytes.
Eight DIMMs, or DIMM sockets. Okay. I would say two network interfaces. So this is sort of hit the sweet spot of, I would say, yesterday's 80 percentile server. So things have changed. So yesterday it was 1 gigabit. LAN on motherboard. So this is what we embed in the in the printed circuit board. So this is yesterday's. Today, well, I'll just modify it with another color. What is today's? What is today's? No, that's green again. It's blue.
Mike, do you see right behind you on the shelf there?
Yeah, this will work. This will work. So what has this gone up to?
16.
This has gone 8. Not for the flagship, not for the 80 percentile server.
12.
The maximum has gone up to a little higher than what the sweet spot is, but there's a certain sweet spot that's not quite high as 16 or 18. It's close. It's 12. So that number's gone up to 12. And what has this gone up to?
4.
Okay, that's gone up to 10.
Yeah.
10 gig for some of us. Not everybody is embedded 10 gig technology. So this is what it's gone up. So this is what it looks like today, and that's going to change in the future. So how we define what the 80 percentile server is, flagship product, is going to change over time. So why do you think these numbers have changed from yesterday to today?
User impatience.
Yes.
Instantaneous is not fast enough. Go faster.
Yes, got to go faster.
It's memory support for virtualization.
Yes.
But Ethernet
Yeah,
allows you to-
so virtualization. So virtualization yesterday was not part of the equation. We didn't virtualize like we do today. So virtualization is something that's driving this, and also number of CPU cores. So before we never had, we had one core, and then we went to dual core, quad, and now we continue to go up to 12 and on up.
Today
So-
we've got, we passed around a 12-core processor for x86. That's the biggest one. That's the one that looks like a rectangle. That's an AMD 6100 series processor. It'll go up to 16 cores in 2011 with AMD's Bulldozer architecture. So we're talking 2011 with 16-core processor.
Yeah. So there's a few things out there that are driving these technologies. So virtualization was never part of it until now. Now it is. Now it's a major part of it. Number of CPU cores. So we have to feed the beast. So we have to increase the amount of memory. And if you're going to create an environment that's optimized for virtualization, now that virtualization is a reality, we also have to get back to what Dan has been mentioning all along, is a balanced architecture. So if I increase the number of CPUs, or the cores, I should say, if I increase the number of cores, I also have to increase the amount of memory. If I increase the amount of memory, I also have to increase the amount of I/O. I have to have all three. All three pieces have to exist for a balanced architecture and to make or to optimize for virtualization. Okay, and an I/O, what I include in I/O is anything that's not memory. So that would include networking and storage. So let me put that in. Okay. So one of the things, in fact, let me ask a question. What kind of cell phone do you have right there?
It's a Samsung Galaxy.
Samsung Galaxy. What do you have?
Android Nexus One.
Okay, Android.
Yeah.
Okay.
Or Google's Nexus One from
Yeah.
HTC.
So what's the hardware though? Android is the OS. What's the
HTC.
HTC? Okay.
Yeah.
All right. And what do you have?
iPhone 3GS.
iPhone 3GS. I have a BlackBerry, but I took it off for this occasion. You have an iPhone too? Did you know that every single one of your phones, and this is a discussion that me and a colleague have been having for the last several weeks over the Christmas break, did you know that the architectures on every single one of your cell phones are almost identical? Right?
Meaning what?
Meaning they all have a CPU, they all have memory, they all have an LCD interface, they all have a keyboard interface. But the experience between an HTC phone or an Android or a BlackBerry or an iPhone are very different.
Yes.
So it comes down to the implementation. So we have essentially, so I would imagine that the cell phone companies have, essentially they're locked into the same sort of architecture where they have memory, screen, and keyboard. So there's going to be some variations when you start talking about applications and user experience. Are going to be very different. So it depends. So I guess my point is, it comes down to implementation. Let's transition to server architecture. So since we're all between IBM and Dell and HP and Cisco, or anybody at Supermicro or anybody else that wants to get into the server market, pretty much have the same architectures. So what are the differences? It is the implementation that defines the user experience. So there are some things that it's just not well known about what HP does in terms of implementation. And that's That's why, you know, Dan's here, that's why we're all here, trying to talk about what those differences are. So architecturally, we're almost identical. We have to be, because we use the same Intel chips, so the same A&D chips, or even the support chips, the same RAID controllers. So we're kind of tied into this same architecture, but the implementation is very different. For those of you who have been server admins in the past, know that user experiences are very disparate when it comes to that, isn't it?
Yes.
You got a smile on your face. I can see it's something that's resonating.
Yeah. I've had experience with all the different vendors, and they all have different features
They do.
of the user experience.
Yes, they do.
Depending on the drivers, the firmware, and the management software. The management software underpins your ability to support the server without degree in physics.
That's correct. So getting back to this idea of a balanced architecture, we pretty much get the cores for free, or not, I shouldn't say for free, from Intel or AMD, you know, memory from our memory vendors. This is where we have spent an enormous amount of time differentiating ourselves in how we implement. They can't do it in our Blade Center E, they can't do it in Blade Center H, unless they have a mezzanine or a stand-up card. Dell cannot. I think they're saying that they can, but I think they're doing a tremendous amount of testing to make sure that they can get that. But right now they cannot, and it's not because you know, they're not technical experts up there. They just chose not to. It's their implementation philosophy that has driven them to not implement it. And it's something that at HP we had the foresight.
And sawed it right in half. So this is an internal cutout view of what the blade looks like, or enclosure looks like on the inside. Mid-plane is right here, and it
Did you want to talk about it, Dan? Okay, you want me to go ahead? True 10 gigabit per second midplane. As you can see, it's sort of if you look at the cutout or the chassis that's been cut in half, we affectionately call this a C3500. Are the midplanes. So it's our connection point that connects the peripherals in the back and the fans and also the servers in the front. So it's a very important piece of the entire infrastructure is the midplane. Lifespan. And one of the things that we always do is we're always looking at new technologies to find out what sort of technologies would preclude this midplane or this chassis. And so far, you know, looking at solid-state drive technology or looking at Ethernet or fiber channel over Ethernet, there's nothing really that prevents us. And it's because of the engineering that we did way back in 2003 that said we got to have a midplane that can support 10 gig switching that allows us this flexibility, this freedom, 10, 12 years down the road. So this is the
And that ties back into what, the Cowboys were looking for yesterday, right? They wanted a roadmap that was going to last them, support them out 7, 10 years. That was specifically one of their selection criteria they asked for, and this is the sort of thing we're talking about. And and it's not just 10 gig, right? We're supporting 40 gig independent band today, so probably.
Yeah. So 40 gig InfiniBand, but the way we do that is we use quad data rates. The line rate is 10 gig, but we do things like double data rate and quad data rate that allows us to get to 40 gigabits per second.
Could you talk a little bit about the blade technology that the Cowboys are using and like why they did select our technology versus one of the competitors?
What? Were you there?
Yes.
Ken? So did you wanna enlighten us as to?
I think it's just things like this, right? We talked about they wanted to put that infrastructure in place and be able to grow and expand and support their future needs within the existing footprint, not have to replace that infrastructure. So just changing out I/O modules in the back of the enclosure or blades in the front of the enclosure as they needed to grow, that infrastructure is going to live, right? It's not going to be I've got to rewire this whole rack or replace this whole rack. It's just within the enclosure I can meet the needs.
So, if I were to guess, Dallas Cowboys, are like any data center, and virtually any customer that has, wants to go into a bladed form factor. And the number one reason that customers buy blades is because of, I shouldn't say number one reason they buy blades, but I would say the number one problem that IT managers have is cooling. The number two problem is power. Number three are cables. And down the list is management, and
When you say cables, like where to put them, front or rear?
number
Or
of
just
cables.
number of
The rat's
Yeah.
nest.
Okay.
Yeah, it's
Yeah.
a rat's nest.
It's a huge rat's nest. In fact, if you came and went behind just those three racks before Christmas, you could have seen what a rat's nest looks like, just because we're not good examples of how you should run a data center here in our little lab environment. But the reduction of cables is tremendous when you step into a bladed form factor. For example, one of our marketing numbers we always say is with Virtual Connect, our technology, you can reduce the number of cables by 94%. And I'm like you, when I see marketing numbers, I'm like, come on, 94%. What that is it's assuming a pass-through of 16. So if you had a bunch of 1U boxes, or if you had a pass-through in a C7000 chassis, it's assuming you're going from 16 cables down to 1, which is entirely possible. So talk about reducing the number of cables in an environment and in a full rack. You multiply that by, the number of chassis in a rack and the number of cards inside the chassis. The number is just tremendous when you talk about reducing the number of cables. So it's just a huge deal. And the reason why it's such a huge deal is because it's almost one of the whenever you have any connector in any system is one of the places where things fail. So that's true inside of a computer chassis. It's true in a data center. So whenever you have a connector, you introduce humans pulling out cables, or for some reason the connector not making a good connection. So we want to eliminate as many of those trouble spots as possible and make it easier to manage. So it was number 3 on most data center or most IT managers' lists. So they probably had a huge rat's nest, or they had some problem they wanted to solve with cables or power or cooling. So, okay.
Let's talk about some different technologies.
Okay. Yep. Sounds great.
We talked a little bit about the enterprise data center, who's doing a lot of virtualization. They're using the 80% server, so we balanced that. Let's talk about another Proliant here for a minute. Anybody recognize this?
Yes.
What is it?
It's the baby Proliant.
The baby Proliant.
That's right. It's the
Oddly, that's not the
microserver.
brand name.
No, it's called microserver.
The microservers. Anybody used the microserver? This is the perfect first server as we like to describe it. Single processor, just the right amount of processing capacity, memory capacity to run, those first applications that you need to run on a server. And yet, it's truly a Proliant. It's truly a server. It's certified with the server operating systems, uses the technologies like ECC memory, and yet the price point is extraordinarily low because it's your basic server. In fact, I think in the UK, they're running some specials over there that are sub 100 pounds.
Now they've been getting interesting reviews. They're really cool.
What do you think about this kind of platform?
I think it meets specific target markets. It could also be an interesting thing for home use. It's a fine starter server because it's very small. Don't need to wreck it or worry about it.
Dan, do you know the US list price by any chance?
I just looked yesterday. It's $329
$329.
on HP.com. Started.
Inside it varies depending on what hard drives you put in there. It has 4 cold pluggable hard drives. I'm actually running a server 2008. It does in fact run ESX. Not you shouldn't be doing that on a server that small, but it does run ESX. But it is truly a Proliant. An example I want to talk about how we develop our Proliant servers, whether it's this microserver, all the way up through our blade servers and up to our DL980, that's our 8-socket pre-melt-based server, is that they all go through the same test and qualification process from our engineers. Most of the Proliant engineers are, in fact, here in Houston.
Yeah.
Some of them have been here since the very first Proliant days. If you go back to the System Pro, which is more than 20 years ago, the first x86 2P server.
I was there. Yeah.
One of the things that we developed when we were working, in fact, I worked a little bit on the System Pro. One of the things we developed back then were a lot of the same tools, Smart Start, for example, way back then. Some of the test tools that we have developed over the past 20 years are actually some of HP's most precious intellectual property. And in fact, I'll tell you a little bit about one of the Proliant team's most closely guarded secrets in terms of our development process. Which is actually a tool called Meat Grinder. This is a tool we've developed over a couple of decades, which is feared, I would guess I would say, in the industry because of its ability to diagnose, spot, and find problems while servers are being developed. It finds, for example, problems in processors. It finds bugs inside processors. It finds bugs inside network controllers. It finds bugs in operating systems. It does this by running every imaginable instruction that a server can do in a very coordinated, multi-threaded environment so that we can replicate any random or arbitrary sequence of instructions or commands. For example, running on a microserver, we'll have simultaneous threads running in that test out the CD-ROM, test out the processor cache, test out processor core-to-core communications, test out drive reads and writes, and do this down to the lowest level of detail. This Meat Grinder tool, like I said, one of our most closely guarded secrets, finds those bugs before the products ever get into production.
It just spawns an enormous number of threads and does a very large-scale system test. And people have heard about it over the years and just never, like Dan said, it's just one of HP Proliant's crowning jewels.
Assume it's similar in concept. If I don't know if you guys know about it, but BCS has Hazard. You guys are aware of Hazard? Is it similar in concept to Hazard? Same kind of thing where it's like legendary test software that just finds every bug it can possibly find in it.
No.
I'm not familiar with Hazard, but that's exactly what it does.
Yeah.
In fact, there's an HP UX version. Actually running that. In fact, if we get a little chance, I'll show you a little demo of it, because in fact I've got it running on this microservice. And like I said, especially the processor guys fear Meat Grinder because it finds those nasty little cache coherence bugs.
Wouldn't that be a reason for them to incorporate, hey HP, test this chip?
Obviously, we work extremely closely with AMD and Intel on the x86 side very early on in the development cycle for those kind of things so that we can joint testing and find those bugs.
Yeah. We've been validation partners for a long, long time. With Intel.
Not that I know of.
Intel and AMD both brings things to the table, which is why we're committed to doing both Intel and AMD in our x86 Proliant designs for the long haul. For example, we've got over here a DL380, which is a 2-processor Intel-based server. In fact, it's the most popular server in the world. And then right next to it is its sister product, the DL385. Almost identical, except uses AMD processors instead of Intel processors. In fact, if we get a chance, we might power those suckers up because we've got a bunch of benchmarks loaded on them. And we've got the max processor on either side. So we've got the best AMD processor in there and the best Intel processor, so you can see what they look like. There are times when the Intel processor is more appropriate for people that choose that one. There are times when the AMD processor is more appropriate for people that choose that one. You've got to have them both because, just like I said, some workloads run better on one than the other. It's, like I said, it's kind of like Laverne and Shirley for you folks who've been around for a while. You got to have both. Because if you don't, if you just have one, it's a boring story. If you have both, they work together.
It's like Shamil and Shamazel.
Yeah.
I thought you were talking about beer and Pepsi, or no, Pepsi and milk.
Oh.
Oh, yeah.
You really want to get that deep on Laverne and Shirley?
And Lenny and Squiggy. And, oh gosh. Like I said, I've been working on this server for 20 years now. So.
Apparently when he's done working, he goes and watches the Laverne and Shirley videos.
So we've talked a little bit about the need for the balanced architecture. We've talked a little bit about some of the components we use, memory, processors. A lot of those are standard components used across the industry. It's how you implement them to make some of those differences. How you develop these products using things like Meat Grinder and the other tools that we have.
Well, I kind of wanted to, if there's time, to talk about a little bit about our cooling strategy, because you asked the question about, or at least it made me think of this, or at least go down this direction, is the number one problem that data center managers are trying to tackle, and that is cooling. And HP has taken a very unique approach to cooling our blade system than any of our competitors have. Let's look at this again for just a moment. If you look at and I'm going to go right on the board here in just a moment, but I want to point something out here. There are three unique different airflows inside the C7000. This is the server area, and there's airflow from front to back, and we use what is called negative air pressure, which means fans at the back, we draw the air across the devices, as opposed to positive air pressure, where you push the air over devices to cool them. We use negative air pressure, as does all our other competitors do as well. But you have negative air pressure in the server area, which is drawn through the server blades and through these trap doors. There's little doggy doors, top and bottom, and only one is actuated with a half-height blade, and two are actuated on a full-height blade, and it allows air to flow from front to back into these little chambers and through these little level-or blinds and out the fans. So these little chambers. And one thing that HP has done in the C7000 is we've created a closed-loop system, so that if you pull out a blade or you pull out a fan, it's going to seal off that airflow from its neighbors. One of the things that you don't want to have is, if you pull out a blade, have a low resistance air path from beginning to end. What that means is you'll experience blow-by. That means all the air that you're using to cool the chassis is going to go down that low resistance path, and it's going to starve the neighbor from getting cooler air. So some of our competitors have a time limit. So if you pull out a blade, you got 2 minutes to make that repair. In the C7000, it's not the case. We close things off, make sure it's completely closed loop. So again, it comes down to implementation. Yeah, we've got the same tools, the same sort of architecture, but we chose to say, okay, user, or Mr. Customer or Mrs. Customer, you can pull out a blade and you can stand there indefinitely, and we're not going to starve the neighbors if you pull out a blade, because of how we implemented the cooling strategy. So we have one area where we have its own isolated air, and then we have power supplies at the very bottom where we have airflow from front to back. That's separate from the server area. And then the challenge was, how do we cool the I/O cards in the back of the chassis without using preheated air? So if you look at the front of the chassis over here, you'll notice that we have two slots on either side of the C7000. On either side of the C7000, this draws air from front to back. It goes along the inside wall of the chassis, and let's see, where's the oh, sorry. It flows along the inside wall of that chassis and comes to the very back and is drawn into these holes. So every I/O module has holes on either side where air is drawn into it. It goes back toward these little chambers and then out the fans. So it kind of takes this little scenic route and then out again. So that was one of the things, the amount of engineering that we had to do to make sure that we didn't use preheated air to cool the I/O slots, the I/O interconnect. Okay, so one of the cooling philosophies that we've chosen for the C7000, and this is something that proves, or hopefully I'll demonstrate that we've been thinking about a lot of things, not just the server, but also the server environment and the data center environment. Somebody years ago told me that if you want to design a computer, the way that you have to approach the design is look at one level of abstraction higher than what you're designing toward. So if you want to design a computer, look at the environment in which it lives in. And that's something that we absolutely have done with the C7000. So if you look at HP, and I'm just going to say the others. We don't need to name names, but I will.
Oh, excuse me.
Oh man, all over me.
Trying to say that that particular one is messy or what?
Oh no, I'm
No.
sorry. Just there's
Okay, so in terms of cooling or airflow, we've chosen low volume and high pressure. Whereas the others have, and they're varying degrees, but they have high volume and low pressure. Okay, so let me explain what that means. So if you have a server blade, this is called delta T. So delta T stands for change in temperature. If this is your input ambient, so I'm going to say this is T1, this is T2, and so input air comes into the front of the blade server and out the back. And hopefully there's a change in temperature. In HP's case, we are anywhere between, depending on the workload, it's going to be anywhere from 30 to 40 degrees Celsius. That's a rough number. Don't quote me exactly on what that is, but it's a lot higher than any of our competitors. I did a power test on one of our competitors. The delta T for them was about 9 degrees Celsius. Very low delta T. So what that does, and we've had competitors come up to our customers and say, okay, stand behind the HP box and put your hand in the exhaust air and feel how much heat the HP box generates. Okay, now step over to the other chassis and you can see how cool it is. See how much cooler we run? So you're paying a lot of money to cool an HP box versus somebody else's box. So let me explain to you why we do that. Now, earlier we said we had the same architecture, essentially, and we have implemented it a little bit differently. So if you take the same processors, the same DIMMs, the same NIC chips, same management, you're essentially going to have the same amount of power. Let's just say, for argument's sake, that they're identical between us and everybody else. But if you stand behind an HP box, it's going to be a lot higher in temperature than it will anybody else's. Let me explain why. Okay, low volume, high pressure. So what we've done, and what I've just shown you over here, is a closed loop system where we, since it is closed loop, and you look at a server blade that's a production blade. You got one that's got all the. Oh, this is a good example. So if you look at this, these plastic pieces, these heat sinks are considered high impedance devices in terms of airflow. You cannot push air through plastic. It's going to go around it. So if you think of like these two heat sinks as two big rocks in a river, water is going to flow around it naturally. So our challenge as airflow engineers is to be able to push air
through those rocks, or essentially through those heat sinks. So how do you do that? The only way that you can do that is you increase the pressure differential between the front and the back of the chassis, and we slow it down, we slow the air down, and we direct it exactly where it needs to go. So these little plastic pieces that you see in your box for years and years and years that you throw away because you don't think they provide any value, well, they absolutely do. And what they're doing is they're increasing the impedance of your blade or of your system, and they're directing air exactly where it needs to go. So if you look at,
I feel like the mattress tag.
oh, here's a,
Pretty much, yeah.
okay, so yeah, let me
Do not sort of move under
So if you look at the HP, we've chosen as a design philosophy to slow the air down, and decrease the fans, and increase the pressure. The way that you increase the pressure is you have to increase the tolerances on your sheet metal and make it a closed loop system. Other competitors have chosen to make a very open and a very airy system. So in order to compensate for that loss of air, because there's air going places where they didn't anticipate, you have to compensate by increasing the volume. So you have to increase your volume, and as a result of an open and airy chassis, you increase the pressure. So that means that your overall system power is going to be a lot higher in this case than you will in this case. So what happens is, as the air molecules travel through the server, it goes slow enough, we directed it exactly where it needs to go, it picks up more heat per air molecule than anybody else's. So by the time it gets to the exit, it's a lot hotter than our competitors. So what you can say, instead of saying HP generates a lot more heat, we're getting more heat out, because we're slowing the air down, we're picking up heat, and then we're removing it. Now, contrary to popular opinion, your crack units or your computer room air conditioning units like a high delta T. It's more efficient if you have an input temperature that's way hotter than the temperature it needs to provide. And the first time you hear that, you think, that doesn't make sense at all. In fact, I had somebody from, I can't remember, somewhere in Phoenix, and he called BS on that. He said, there's no way. You've got to be lying to me. And I said, you go ask your facilities guy, and you get back to me. Here's my card. And he was here on a briefing in this very room. He was so excited. He was giddy. He was so excited to see me because he said, you're right. I didn't believe you. And my facilities guy said, yes, we want higher temperatures on the exit than, and we want high temperatures to feed into the crack units. That's something that HP has been doing for a long, long time. And other competitors don't understand that. They're just now starting to figure those things out. And that's something that we've designed to for a long, long time. And what this gets to is when we say we're going to have a low volume, high pressure box, that means those are things that are directly attributable to utility costs. So it's going to be a whole lot cheaper to run. I guess this is why it's important to you, is because it's going to be a whole lot cheaper than it will to operate these boxes. Well, then if it's a lot cheaper, why isn't everybody else doing it? The reason why is because the manufacturing costs are too high. It costs a lot to have sheet metal with very tight tolerances. And so the manufacturing costs are a little bit higher for us, but we pass the savings on to you in terms of operational costs. And it's because of the cooling philosophy we chose.
What percentage higher? Do you know how much higher it would be, or?
For what? For the sheet metal tolerances?
Yeah.
I don't know. I don't know.
Okay.
So I don't.
Because
know
I'm
that
just
number.
trying to figure. You figure manufacturing, yeah, higher, but return on investment. How does that come into play? I'm assuming it will.
Well, you look at the where is the let me look at the Cisco midplane, for example. It doesn't come just to sheet metal tolerances. It comes down to design philosophy too. Look how open this is, and you would think, wow, that's so open. And you look at the HP midplane, and it's a solid piece of printed circuit board. This seems like, to me, this would be easier to cool because it's wide open. Well, when it's wide open like that, it's very leaky. That means it's low pressure, and I've got to spin those fans up a lot higher. So, so what you do is you end up having a low delta T and you have this wind tunnel effect, essentially. So the air never really has time to pick up any heat as it goes through the chassis. And essentially, this is the electrical equivalent of a short circuit. That's what that is. So, so it's not just sheet metal tolerances. I don't want to mislead you. It's also, you know, they consciously decided to build a very open and a very airy chassis, so they can make it a little bit cheaper. It's got, you know, less printed circuit board. It's supposedly easier to cool. In fact, if we have in our mechanical lab a big giant blue lab instrument called the iron lung, and it's nothing but a fancy airflow meter. And what we do is we take a chassis, we run, I think we run Prime 95 on it, which is something you can download off the web, and it's just a you know, a generic stress tool. We run Prime 95, we hook it up to the iron lung, and we run air through it, and we determine how much air you can push through a servo chassis or a servo blade. And it turns out that Cisco was among the highest. You know, the M200 was about 57 CFM, and the BL460 was about 20 CFM. So what that means is that you can't. We have more resistance in our path than they do. And when you look at it, you think, well, Cisco's better because it's easier to push air through it. You look at a Cisco blade, for example, you see how open it is. So you see these low resistance paths from front to back that go all the way to the back, and they're unrestricted. So this is where you start experiencing blow-by. And what needs to happen is you need to block that free air that's going from front to back and move it toward the processors or toward the heat sinks. And since a significant percentage of air goes right by these big rocks or these big impedance items, you have to compensate and increase the amount of air that will go through by increasing the airflow or increasing the volume. And this will increase your overall system costs as a result. So these are just some of the little things that HP is always noodling on, always working on, always trying to fix, always trying to optimize. And we've been doing it for quite a long time. You know, Dan said we've been in the server business for, you know, since the System Pro days, which 1990.
It was 89 when the System Pro came out. That was the first x86 server, but then
Yeah.
prior to that, it was HP and DEC and other components of the HP portfolio and servers for a lot longer than that.
So you know, these are problems that we've been noodling on for you know, about 20 years, and we think we understand how they operate inside of a data center. And some of these blades that have just shown up, you can tell there has been no thought put into power and cooling.
Hey James, I don't know if this is an impact or not, but it seems if we're taking more heat out than they are, then they're running a lot hotter, and that seems to me it might have an effect on reliability, because if things are running hotter inside, is it first of all accurate to say it's running hotter inside?
I would say that they're probably not running hotter inside. I'm saying that the reason why there's overall system power is higher is because their fans are running a lot harder than our fans. I imagine that they're going to keep you know,
the inside temperature still.
Yeah, the inside temperature still, yeah. So that's the variable. So the inside temperature is probably, you know, it's one thing that I didn't record when I took the power tests, and I wish I would have, because I get that question all the time, is I guess it's implied that, you know, maybe the inside temperature went up, but I'm guessing because the fans spin up so aggressively that they kept the CPUs at a...
From getting too hot.
Yeah, from getting too hot, and they kept them, you know, away from that threshold. So...
Yeah, makes sense.
That's what I assumed. But
You got to talk about the larger implications, what that means across a data center, having all that warm air as opposed to a little bit of hot air.
well, you know, yeah. So you know, with scaled architecture, you have scale problems too. So they only compound. Is that? I mean, you can go ahead and add to the discussion if you like.
Well, so now you've got a whole bunch of hot air coming out the back of the enclosure. You think of a little bit of air versus, you know, 2-3 times the volume. You're going to have a lot greater chance that you're going to have warm air infiltration from your warm aisles into your cold aisles. So now you've got Again, you've got the short circuit happening at the data center level as well as at the within the enclosure or rack level as well. So you're just building on layer upon layer of inefficiency in the system.
That's right. Okay. Yeah. Thank you so much. I appreciate that. Any questions at all? Has anybody seen that test being done? Do you walk behind? Do you walk data centers very often and put your hand behind computer gear and find out, wow, you could fry an egg on that? Yes? No? Why don't we transition over to?
Let's talk something a little bit different. Let's talk graphics. I got two examples I want to show you. This is a blade. Looks very much like the 80 percentile server that James was talking about a minute ago, but there's something that's special inside of here. Put this thing up, and there is in here a mezzanine card. Now, unlike most of the mezzanine cards that are in a blade server, like here is a network card and a fiber channel card, what this mezzanine card has on it is actually a NVIDIA graphics controller. This is a workstation blade. It's used for, among other things, delivering a high-end graphics desktop to a remote end user, and yet all the compute, including the graphics, stay inside the data center. It's managed just like a server, except it's running client operating systems. Another use for this, a new use for this, is something like Remote FX. So have you seen Microsoft's Remote FX in 2008 R2, I guess with Service Pack 1? Your ability to deliver multiple desktops to end users delivered from a server compute engine, and then each remote desktop basically gets a sliver of the graphics processing unit that's inside the server. So that's a way that we're incorporating not just server technology, but also desktop technology into blades. Let's talk graphics in another environment over here. This system over here is our SL6500 series of servers. Has anybody heard of the SL line of servers or scale-out line before?
Yes.
What do you know
Well, you've got 6000, 6500. They're used for scale-out, so you can have in one new format 2 servers, because you cut the server in half. So it's like a mini DL360.
In some ways, it's like a rack server. In other ways, it's like a blade server. Traditional rack server, for example, right here is a DL380. Front accessible are basically the buttons and the hard drives. On an SL series, designed for scale out, front accessible includes virtually all of the cabling. It's front accessible. It allows, just like Martin was saying, half-width servers, so that you can get even higher density than you could in a rack format. And it does something I wanted to show you about related to graphics processors here. This is a new SL390S. Those heat sinks. This is a 2-processor server. This one uses Intel processors, a bunch of DIMM slots. But there are 3 of these big heat sinks in here. Any idea what's behind these things? GPUs. That particular server has 3 NVIDIA. It's a Tesla 2050, I believe. So each one is just about 450 cores for running massive numbers of floating point instructions and other things that you can do with the GPUs. There's a version of the there's a version of that, the SL390S, that actually can put 8 of those GPUs inside a single server. And then using like the NVIDIA CUDA technology to be able to run some of those applications on the GPUs, you're able to get into the billions of flops and run those applications, oil and gas stuff, biosciences stuff, that the supercomputer guys like to run on are starting to run on the GPUs rather than the CPUs. So we deliver that in an SL form factor, a scalable form factor, for those folks who are deploying, not just 1s or 2s, but dozens and hundreds of individual nodes so they can build those clusters out. So 2 interesting uses of graphics inside the server portfolio. I'm going to do a time check here.
She said we got about 40 minutes.
Okay, cool. Good. We've talked a bunch of different random server technologies, but once again, I want to say, what do you guys want to talk about next in terms of Proliant server technologies?
Now that we've plumbed the pipe and got the juices flowing, and now you've got all kinds of questions.
What's next?
What's next? We're not here to talk about futures today, but I can give you a brief glimpse into what's going to happen. Obviously, we are going to continue to deploy some of the industry's most powerful servers in terms of Proliant for the next, as far as the eye can see. 2011 brings a lot of interesting technologies. Both Intel and AMD have new processor technologies coming out in 2011. Intel, a couple of different families, part of their Sandy Bridge portfolio. This is their next generation of processors to follow on to today's so-called Westmere processor. Adds core counts, adds some additional new features, including, for example, Intel's servers implementation of their Sandy Bridge architecture includes, like I said, more core counts, higher memory capacity, and they're also integrating more devices into the processor complex than they did before, including, for example, possibly a SAS controller into the CPU complex. AMD's got new technologies coming out in 2011, including their Bulldozer core, which brings a couple of new processors, including, on the server side, a 16-core interlogos processor. So you can expect to see HP supporting both of those processor families in 2011. Other new technologies coming out in 2011 include larger capacity and lower cost solid-state drives for use inside servers. Some new networking technology should mature in 2011. I know we're expecting to see improved bandwidth on InfiniBand with EFR InfiniBand in 2011, and that not quite doubles the 40 gigabits per second of the QDR InfiniBand. I think it goes up to like 56 gigabytes per second. We talk a little bit about another new technology that's actually already hit us now. A lot of modern servers include a RAID controller. This one's got one in there, so you can do just simple RAID, one array on a couple of hard drives. Inside the RAID controller is a cache module. It's built on memory, either memory. And for HP, what we've done for a number of generations now is we actually put a little battery that's attached to that little controller. Let me explain a little bit about that. The idea, basically, if something goes wrong, that battery will make sure that you don't lose any data. It'll make sure that the data sticks around in the memory until you can recover from it. But there's been a new technology that came out last year where rather than having memory attached to a RAID controller, we use flash to attach to the RAID controller. So your cache can be flash backed. What this means is, in the event of a system failure, any data that hasn't been written to the drives, rather than depending upon a battery keeping it alive until you can recover, it can actually be stored in the flash device, which effectively has an EEPROM life. So you'll see more technologies like that coming out in 2011 as we adopt more flash technologies, especially the price of flash, NAND flash comes down. What things do you see in the next few years that interest you?
SSD, just like you said. Well, you guys have always been on the forefront on figuring out how the cables really should be going into a machine. So, as hopefully we'll get smaller cables, less cables coming through, so more room for design and airflow.
Okay.
That's a good point. When you talk about SSDs, you look at a normal 2.5-inch drive. Do I have an SSD?
they look identical to that.
They do look like except they're a lot thicker. If you look at the, and I hate to keep on going back to power and cooling, but I hope you're interested in that. But if you look at the thermal design envelope of a normal 2.5-inch hard drive, it's about 12 watts, and it has to be out in cool air. It's spinning media. It likes to be doesn't like to have preheated air go across it. So that means since it's 12 watts, and I've been on I was on a design team years ago, and a generic rule of thumb is if it's over 5 watts, it needs a heatsink on it. So if you look at chips on a board, and you see heat sinks, you can almost guarantee that they're above 5 watts. If they don't have a heat sink on them, then they're probably under 5 watts. If you look at a hard drive, they're 12 watts. There's no heat sinks on them, but they've got to be in fresh air. So once we transition to solid-state drive technology, the thermal design point goes from 12 down to 2 watts. So once it goes down to 2 watts, what that does for us is it gives us design flexibility. No longer do I need to put it in fresh air. No longer does it need to be out in front. I mean, hot pluggability, yes, we'll always probably have, that's sort of one of HP's trademarks, so we'll probably always have models that have hot plug drives, but it doesn't need to look like, 2.5 inches by, 4.5 inches like these small drives do. They can look like almost anything we want. An example is Fusion I/O. Have you heard of the Fusion I/O module?
Yeah.
And what do you know about it, Fusion
It's a
I/O?
PCI card that you can plug into a blade or a server, in theory, and that gives you very fast read-write performance.
Yes.
We were talking a little bit about that as analysts.
Yes. And it's been used in a number of scenarios, but one of them is if you're wanting to have very fast writes or very fast data caching, you can offload the data onto SAN or something else afterwards. Something that I've played with, but not extensively.
Yeah. So, I mean, something that Flash or SSDs give you, especially the Fusion I/O module, is if you look at in terms of access times. If you look at a normal hard drive, it's in milliseconds.
Yeah.
Memory access times are in nanoseconds. So this is 10. I know I'm getting geeky here. I apologize. And this is 10 to the minus 3. So this is a lot slower than this. Is very fast. So you have memory access times that are in the nanosecond range. Hard drive access times are in the millisecond. And then flash devices are here at 10 to the minus 6. So they're in the microsecond. So they change 3 orders of magnitude faster, and that's continuing. So you're going to see this as these kind of come together.
Well, because it's for low latency applications, for HPC, for low latency trading. That's where it can be worth, instead of using combined Fusion I/O as the dumping ground, where you write everything and say, okay, I confirm that trade's gone through, or I confirm that risk has been priced and the value is X. And then you can offline it afterwards. But it's for instant write performance.
Yes, yeah. So it's I mean just the technology and just the speed up of of storage is just impressive. I don't know if you've ever installed an operating system on a flash drive, but it's like it's so fast you think something's wrong. It's like there's no way it could have installed in minutes rather than 40 minutes or a half hour. So this is one of the things where it's changing how we look at computer systems, because not only is it a lot faster, but it's a lot smaller. So we have this chassis. When we talk about longevity of the chassis or what's next, we're looking at also what's next and what we can put in this or what this chassis is going to support. And that's why we keep on extending the date out from 2011 to 2013 to 2016, and that is a minimum commit date. That means if we get closer to 2016 and there still isn't any technology out there that's going to preclude this chassis, we're going to extend it again, as long as it has life. And in fact, solid-state drive. In fact, we're looking for technologies that may preclude this chassis and say, "Oops, you know what? That's a brand new technology. It'll no longer be supported in this. Let's transition to an entirely new platform." We haven't found that yet. In fact, transition from spinning media to solid-state drive technology only gives us design flexibility.
The same is true for I/O. We start with, if you look at the back of the chassis, if you were to try to adhere to VMware's guidelines of having anywhere from 6 to 8 NICs per server, and you were to accommodate that requirement, it would require you to have 6 interconnect switches plus 2 2 fiber channel switches at the very bottom. So we have to fill out the entire back end. With Flex 10, how many are aware of Flex 10? You're the Virtual Connect Flex 10 module?
We're going to talk about that next after this session.
Oh, you are.
Renix and Microtosky.
Oh, they're going to talk about the Flex. So let me just, I won't baptize you in it. I'll just, I'll sprinkle you with water. Okay?
No dunking, huh?
I'll let them take care of that. So let me just introduce just a light introduction then. But essentially, Flex 10 is our second generation virtual connect technology that has persistent MAC addresses, persistent worldwide names that stick with the slot and not with the blade. Okay. One of the things that Flex 10 allowed us to do in the Virtual Connect family is to be able to divide up a 10 gig NIC. So what I've done, this is a 10 gig NIC, and we're able to now divide it up into 4 different NICs. This is all embedded. So instead of having just 1 NIC, I now have 4, and I can allocate variable amounts of bandwidth per section. So I can assign 5 megabits here, 2 megabits here, 2 megabits here, 5, 6, 7, 8, 9, and 1 megabit, say, for management. So a vMotion, public and private, and a management network. I can now have 4, and they each have their own separate MAC addresses, and the operating systems, regardless if it's ESX or if it's Windows or Linux, they're going to see 4 adapters now that you can use. Now, one of the architectural decisions that we made is anything that's embedded in the C7000 and it's Ethernet related, it's going to come out of the top row. End of story. It's hardwired. Nothing you do to get around it. So if now I have 2 NICs in the past, I now have, since I have 2 NICs embedded, I now have 8 NICs. Those 8 NICs still come out of the top row. It's not going to go to any of these other rows. What that means to you is instead of having 6 interconnect modules, I now reduce those. I can reduce those middle 4 and go to just 2 interconnect modules in the back and then 2 fiber channel switches in the bottom. So I went from 8 down to 4. The 3rd generation module went from, now we introduced fiber channel over Ethernet. So our Flex Fabric module is the vehicle that we're using to introduce fiber channel over Ethernet into the market. So now, when you go from normal switches to the Flex 10 to Flex Fabric, you went from 8 to 4 to 2. So still, as the technologies have changed, have not precluded the use of this chassis. It just made things easier. In fact, it's kind of what you were saying is we've reduced cables, we've reduced the number of interconnects, we've reduced power, we've become more efficient because we're consolidating. So I know we're talking about converged infrastructure from a data center level, but we're doing it here at the chassis level also. Okay, I hope I didn't steal away Mike Cassie's thunder. So.
I'll look at a lot deeper. Sure.
Okay, who wants to see AMD and Intel go head to head? Want to see that?
I do.
I'm going to need a couple of volunteers. While we wait for these systems to come up a little bit.
I volunteer, Derek.
Wait for those things to come up. It'll be a little bit loud as they come up. I had a question earlier. Kevin Houston, he was apparently too terrified of snow to attend.
Speak to the camera when you say.
Yeah, he's watching.
Kevin Houston just couldn't get in a car and drive to the airport.
Something about a dusting of white powder on the ground terrified him. He stayed home, so not only does he not get a donut, but I decided to go ahead and be nice and answer a question. He'd asked about the SL series. That was the scalable series of Proliant servers. Why they aren't called blades. He makes a good point. Both blades and the SL scalable series are multiple units, multiple nodes that go inside a single enclosure. The enclosure has shared power, shared cooling. There's a couple of differences. Blades handle consolidating the networking inside the enclosure, whereas the SL series doesn't. But Kevin, I think you're fundamentally right. That SL series, this product right here, in my mind, that's a blade. It's got all the characteristics of the blade would. So
Almost.
A good
those
bludgeoning
switching.
device, apparently.
Yeah, almost.
I think getting hit by one of those would be a little bit harder to hurt more than a blade would.
I think when used as weapons, both SL series and BL series probably deliver equivalent damage. So haven't done that in a test lab.
Blades as a weapon.
But if you're in Dungeons and Dragons
Now,
land,
the SLs are longer, so you can get more leverage and more, head speed there.
I've looked. World of Warcraft doesn't include blade server as an allowable weapon. Maybe with the
You gotta check it
cataclysm
out
it does. So what I've got here is a DL385 and a DL380. These are two Proliant servers, nearly identical. The only difference is the DL385 uses AMD processors, and the DL380 uses Intel processors. I've got the highest, fastest Intel and AMD processors, two each in each system. So in the DL385, we've got two of the Opteron 61.
I think we lost Kevin to the Cisco channel now.
6176 processors. What's he doing?
He switched
I
to the
think I'll
Cisco
switch
channel.
over to the Cisco channel now.
He's mad because we didn't give him donuts. So 6176 SE, I think that's a 2.3 gigahertz Opteron, two of them in here, and then X5680, that's a 3.3 gigahertz 6-core Westmere processor. Otherwise identical. I got Windows Server 2008 R2 installed on both of these, and then a handful of benchmarks thrown up here. Benchmarks that we're allowed to talk about or share, or in some cases a couple of benchmarks that are freeware that you're allowed to do full disclosure. So what I'm going to need is two volunteers. I've got one right here. Okay.
Wait, what am I
Tell
volunteering
guy,
for?
really,
what are you signing up for?
Okay.
Lobotomies.
What I want each of you to represent. One of you is going to represent AMD, and one of you is going to represent Intel. You're just going to run the same benchmark side by side, and take a look at the results that are coming out of here.
It's like the Mac and PC commercials.
Mac and PC. So AMD side over here, Intel side over there. So go ahead and command those keyboards and log in. There should be an administrator account, and the password is passwords.
Touchscreen.
You could try.
Yes, you can touch it. Probably not.
It's touch keyboard. It's one of these new fancy touch keyboards. Okay, let's run, I can see a couple of benchmarks here. First of all, let's run stream. So you can mouse, you can head over there and run stream. Stream is a benchmark that measures memory bandwidth, the amount of
How many points do you want to choose here?
choose 16 threads. That's going to be about the best on both of them. So choose 16 threads,
What
and
about
then
the Strad?
leave the others alone,
Okay.
and then run the multi-threaded version. That's probably going to get the most, roughly the most accurate result. These systems are not tuned to run benchmarks. They're just out of the box, basic settings for both. And down, what you're looking at, probably the best number to use is the triad result. So look lower left of the table, you should see a triad number.
So AMD is 34094. Do you want the decimal also?
So it's about 34,000.
Yeah.
And what's the Intel?
24,400.
The Intel's 24,000.
What does that tell us?
So what that's telling you is on the AMD system, your
Big number.
memory bandwidth is on the order of 30% more, 30% higher memory bandwidth on the AMD Opteron two-socket system. And that makes sense, because from an architecture standpoint, you've got more memory channels coming out of the AMD processor. So applications where memory bandwidth is king, you're going to see AMD be doing a little bit better there. Let's go ahead and exit that benchmark and run Cinebench. Cinebench is a kind of a rendering benchmark application. We're going to focus on the CPU tests within Cinebench. So launch that application, and then you should see a CPU test. Click on Run next to the CPU test. So this tests, the system's ability to do some of the kind of graphics rendering. We're not testing the GPU part of the system.
I think you're waiting. Come on, can you speed that up, Jake?
I think it's because this monitor is smaller.
He started his before you.
He did actually start his yours, but
You won. Yeah.
It should come out to be a number, like a
17.
17 for the Intel side.
that's the top number there, the number one.
It should have a number somewhere
oh,
right
right
on
up
the
here.
CPU.
Oh, okay,
Points.
14.59.
14.59. So in this case, for that kind of range stuff, Intel clearly has the lead. Let's take a look at another benchmark. By the way, we could run the single CPU. If you're in the single core version of this benchmark, just running on one core. You'd see very similar results, except it would take 12 times as long, so let's not run that one. Go ahead and close out Cinebench, and let's take a look at
Nova?
let's look at NovaBench. And on NovaBench, look under the tests drop down, and I'm only going to run a portion of the CPU test. So go to the CPU test and run the floating point ones. We'll do the floating point ones, and then we'll come back and do the integer ones.
When are you guys going to come up with
No, I finished
box
first.
test? Right to the ball.
So,
Yeah.
Wow, you came from behind on that one, it looked like.
549 million, 550 million.
550,
622 million.
620 million. So even in this case, for the floating point tests, Intel went out a little bit ahead. Primarily probably because of the frequency. The frequency on the Intel side is higher at about 3.3 gigahertz. AMD, their high-end Maggie cores is at 2.3 gigahertz.
So, interesting though, this says that this has 8 gigabytes more system RAM. So this is not truly a fair test, is it?
It's not quite. It totally close is. The only difference here is on the AMD side, we've actually got 16 gigs RAM. On the Intel side, we've got 24. It's not quite the same. There's an architectural reason why the memory capacities aren't the same. You have to populate AMD 2 processor systems with DIMMs in groups of 8.
Yeah.
Intel, DIMMs in group of 6. So it makes it extremely difficult to do a side-by-side comparison because you can't populate the exact same amount of memory. So what I've done is populated memory so that there's the maximum bandwidth available. And most of these tests are not going to test for memory
Get
capacity.
the right RAM count, you should be able to go. I mean, you go real
If you
high.
go 6 times 8, like maybe 48 or 96 might be able to
Just
do it.
24.
But unfortunately, in some cases, when you get higher memory capacities, memory speed runs slower. So I wanted to run maximum memory speed. Let's do 2 more tests. Run perfmon, performance monitor. One thing that you can do on a Proliant server is through perfmon, Windows perfmon, you can actually read system power. Monitor the amount of power that the system is using.
What, where are we looking here?
We're going to go to the performance monitor little widget.
Okay.
It's a little bit. We're going to add a metric. You press on the play here. Go there. Scroll up in that window, and you should see power right above where it opens up. You should see somewhere for power meter. Select the power meter.
The power budget.
You want power.
Okay.
And then down below, you can select the power meter. There should be one instance of the power meter available. Yeah, you're
Okay.
You're good? You got it right? Okay. Power meter, select that.
Got it.
Now, shift your view over to the report view. So the third from the left icon near the top.
Down.
That's the histogram, one report. One of the numbers should be power. Right now, the system's really not doing anything, so it should roughly be idle power under Windows. All the power management capabilities are running right now.
Yeah.
So what does the AMD system show?
144.
144 should be watts. Or something like that.
Makes sense.
It's what? It's 143. Yeah, it's
Watts.
in terms of watts. And what does the
Okay,
Intel show right now?
118.
118.
117.
117. At idle, Intel's running lower power. And that's exactly what we expect. Intel's got a little bit of advantage running lower power.
With more memory.
No, I have a question. So we have that whole conversation around heating and airflow and that. Is it harder to cool the AMD systems? 'Cause I mean, in terms of every laptop I've ever owned that's been AMD or Intel, the Intel's always run cooler than the AMDs, and I assume that has to be somewhat similar on servers.
The maximum package temperature, like if I grab one of those processors, the temperature at which this little metal part of the processor gets is almost identical.
Really?
Where it's hottest is a little bit different, and it actually matters. But the processors are remarkably similar in terms of their maximum potential power use and maximum temperature. There are some differences, though, and it's very different on a server versus a laptop.
All right.
One last test. There's a different memory capacity in the Intel system than the AMD systems. Otherwise, they're identically configured. Not including... actually, this one is not a benchmark test. This one is a numbers test.
Dan, before we want, I guess to answer your question, from an airflow and a mechanical engineering perspective, to them, they couldn't care less whether it was Intel or AMD. To them,
Okay.
it's just a heat load. And
So the airflow works essentially the
identically.
exact same way.
Yeah, so it's the same guys that are working on the same thing. They couldn't care less what processor is being used. In
I
fact,
just
they,
wasn't sure if there were different challenges because of the way the processors are architected.
there are, but it's more like the heatsink level, like Dan said. There's different points on the processor that get hot, but essentially what they do is they want to make a very clean connection between a processor and heatsink, and have the airflow and all the things that we talked about in terms of delta T. They want to be able to do those things, but as far as they're concerned, they use heat slugs to come up with their They go through their development process, and the heat slug
So all they care about is the heat, not what it is.
Yeah.
Okay.
Yeah. So
Fair enough.
that's how they approach the problem.
One last benchmark.
Okay.
It's going to be the price benchmark.
How are we going to test that?
Well, I've got the numbers here, because we're going to make it more like a game of Jeopardy.
Get
Price is right.
Get out your wallet.
What I've got is I've configured these two systems identically, except for the processors. The memory's a little bit different on those two. Not including the Windows operating system. Not including that, but including all the other stuff, the hard drives, the RAID controller. I've got the U.S. List prices for these two systems. And I'm going to go ahead and tell you that on the Intel side, the list price for this system, and it's roughly equally divided between the system costs about the same as base system costs about the same as one of the processors, because these are the higher-end processors. So including the two processors, all the memory, and the system and all that, U.S. list price is about $8,500. The two highest-end Intel processors, each of those processors runs ballpark U.S. list price about $2,000 a piece.
Okay.
Now, guess is, I'm going to ask both of you to guess what the AMD list price is. 6,000? Guess of 6,000?
5,400.
5,400?
$1.
You go for the price is right answer.
Without going
You're
over.
going to take it home.
List price for the AMD system right now is $7,036. Now, if I account for the fact that there's different amount of memory, if I add about 8 gigabytes of memory to the system, I wouldn't do it because of the performance, but if I did, this number would go up to about 75, a little less than that. So overall, the AMD system is about $1,000.
What if you ran this at 32 gigabytes? I mean, would that be ballpark same price, or is that enough?
Yeah, adding that, it's about $400 to add 8 gigs. So there are many applications where AMD rocks. A lot of them are the high-performance computing kind of stuff, but there are also some standard applications where AMD does extremely well because of their higher core count.
You guys come up with a way to put AMD and Intel in the same box, you would just win all the way around.
We'll come up with a model number scheme for that. The DL382 and a half.
That would actually be interesting in the context of the private cloud stuff that you're doing, though, because provisioning based on what your project is highly dependent on things like what the CPU is.
It'd be a DL38X.
Okay, I think we're getting up to the end of our.
We have about 5 more minutes,
Oh,
so
okay.
if you want
Dan, I don't know if you know the answer to this, but somebody on the Twitter asked, do you know what the list price for the new 32 gig SIM is?
In fact, I don't. I don't know what this price is.
$1 million.
$1 million.
Send it to me. I'll send one to them.
In fact, where is my deal? What happened to that?
Yeah, where is it? Yeah,
Because apparently that one is free because it's gone. So.
Okay, nobody
It's in the
believes my
pile.
pocket
It's
chat.
here somewhere. It is in the file. In the file. It's still in the plastic.
You're just a little late.
I was trying to find
It took a while. Did you use Bing or Google?
I used Google, but now I have it.
Man, that would be great on a blog, wouldn't it?
It would. Until the copyright law comes into effect.
Can 6 notes really be copyrighted?
Yes, they can.
Oh.
There was some. Somebody did ask in one of the chats the specific model numbers of the processors running on each.
Okay. On the AMD side, we've got the Opteron 6176 SE. 6176 SE. That's the so-called 105 watts ACP top-end Magny-Course processor for 2-socket systems. On the Intel side, it's the Xeon X5680. It's a 130-watt processor that runs at 3.3 gigahertz. Turbo mode was enabled, so I think this processor can, at times, jump up to a couple more steps above that, 3.4, 3.5 gigahertz.
Right.
One thing I didn't get to bring in this room was another one of our Proliant servers, the DL980. This is an 8-socket x86 server built with our Prima architecture. Scales up extraordinarily well from the 4-socket side. It's built with the Intel 7500 series processors. We use node controllers on that system to vastly decrease the amount of cache snooping traffic that's going on between the processors. With those node controllers, we can drop that cache snooping traffic down from 70–80% range down to the 20–25% range. So the performance scales extraordinarily well. I've seen some of the benchmarks from SAP, for example, that show that scaling from 4-socket to 8-socket on the Intel x86 architecture. It's not quite linear, but nearly linear. I had a couple of customers already who are enjoying the advantages of that DL980 8-socket platform, including Monster.com uses the DL980s. As an avid watcher of the U.S. version of The Office, I was going to say Monster.com singular.
Not plural.
Does The Office end to start with the Laverne and Shirley jokes?
So I think you answered this, but this is a question on Twitter that maybe be a good opportunity to clarify any confusion that people may have. Somebody asked, how much airflow does the C7000 require compared to chassis from other manufacturers?
Let's see, based on our tests, I wrote it up on the board right there. I broke it down on a per blade basis. So if you look at other manufacturers, they're all in between, but the airflow on the BL460 was the lowest of 460, 490 fell in this category. Others in the test were LS42, which are from IBM, and then the M. So that wasn't M200, that was B200. Excuse me. That's M610. So those were. I want to say this one was probably the highest, and this one was right around the 30s, and 30 CFM. So that's sort of just from our unscientific, tests. This is what we came up with. So it was somewhere in between there. So ours was. You could probably get the least amount of air through an HP blade than you could any of our competitors. Everyone was more open and more airy. Does that answer your question?
I think it does.
And I have one more question from Twitter, going back a ways. Does using the new 32 gigabyte DIMMs drop the clock speed of them down when fully populated?
Using a 32 gigabyte DIMMs drop the clock speed down to fully populated. On an Intel system, the answer would be yes. We're running at 384 gigabytes of memory. I think you're running at either 800 or 1066 megahertz. You have to go look it up. It's actually, it's going to be listed in the quick spec. So if you go out to www.hp.com/server/BL460C, then you'll be able to get a link on the right-hand side for the quick specs. So there's a table in there that will show you exactly what speeds they are. There is also a 16 gigabyte dual rank DIMM available now too, which will allow you to run up to 192 gigabytes at maximum speed. So you can go up to 192 gigabytes running at so-called 1333 megahertz, so max speed with that memory capacity.
Okay.
Any last questions? Sorry, we're about to run out of video, so.
The video camera is about to run out of batteries.
Okay,
All right.
thank you guys.
Okay.
We'll take a quick 5-minute
Here we
break
go.
and then reconvene in here for Virtual Connect Flex Fabrics.
Okay. All right.
Good job.